today what I'm going to do is I'm just going to talk a little bit about machine learning in the context of structural engineering. Talk about not just some of the opportunities, but some of the challenges associated with machine learning applications in structural engineering. You see the title there. I'm not going to read it. And really, what I was trying to get at. So, my group recently completed a state-of-the-art review of machine learning applications in structural engineering. And one of the things we found, as I think a lot of us know, is that a lot of these methods have been around for a long time. It turns out that within the structural engineering community, that researchers started exploring the application of machine learning as early as the 1980s. Back then, the computational power was not as much as we have it now. We didn't have as much data, so the problems were very simple. But today we're seeing in many different fields that machine learning is starting to sort of transform different fields and things like that. So I think it's natural for structural engineers to ask the question whether or not that there can be benefits derived from machine learning. But also keeping in mind that we're engineers, right? So in a lot of cases, we have models, we use physics to derive the relationships between various input and the phenomena of interest. So there's sort of a challenge there, and especially in the case of structural engineering, we're entrusted with the public safety and functionality of communities. So the consequences of errors in terms of our analyses and things like that are much more significant relative to, say, if you're classifying an image as to whether it's a dog or a cat or something like that. So these are all things that we have to keep in mind that makes sort of the exploration of machine learning somewhat of a challenge. I just want to highlight that there's a forthcoming article in Structure Magazine that should be in the June issue that sort of talks a little bit about or expands on some of the points that I'm going to talk about today. This article was co-authored with Mike Mueller. So this is an outline of my presentation. I'm just going to start with an overview of some terminology that we see and we hear, just to make sure that everyone is on the same page. I imagine there's sort of a broad spectrum of there's a broad spectrum of people in terms of their level of exposure to machine learning. So want to try to bring everyone on the same page. And then I'll talk a little bit about the opportunities. When should we be thinking about or considering the application of machine learning in structural engineering? I'm going to talk also about the challenges. There are many, but there are challenges that can be overcome. And with that in mind, I'll talk about some considerations for the future. Okay, so first I would like to sort of distinguish between, like I said, three terms we often hear: artificial intelligence, machine learning, deep learning. They're often used interchangeably, but they actually mean different things, right? So artificial intelligence is sort of the field that is the broadest of these three, right? So it speaks to the ability of machines to perform cognitive functions that are associated with the human mind. So things like perceiving, reasoning, learning, and problem solving. And there's this big debate about whether or not achieving artificial intelligence or human intelligence is even possible, but that's a question for another day. Machine learning, on the other hand, is a branch of artificial intelligence, right? So you can think of artificial intelligence as sort of the umbrella field, and then machine learning comes under that, right? So this is where you're using algorithms to find patterns in data and make predictions about the future, right? So the idea here is that you're enabling machines to learn without providing explicit programming instructions. And there are three main types of machine learning: supervised, unsupervised, and reinforcement learning that I'll touch on a little bit later. And deep learning, which is probably the one that's most popular, this is actually a branch of machine learning that deals specifically with artificial neural networks, which has which has largely been responsible for a lot of the breakthroughs and the popularity of machine learning in the broader society. So as I mentioned before, there are three different types of machine learning. So supervised learning. So this is where you use training data and feedback from humans to detect patterns and predict actual values, right? So an example, which I'll talk a little bit about today, is predicting the drift capacity of a reinforced concrete wall. In unsupervised learning, this is where you're really just exploring unlabeled data without providing any explicit output variable. And really there, you're just trying to detect patterns and sort of describe those patterns. So an example there is if you want to create subgroups of a set of buildings based on structural similarities. And reinforcement learning, which is the one that's probably least popular, but still growing in popularity. This is where you're learning to detect patterns and perform tasks by trying to maximize the rewards it receives for different actions. So for example, trying to find the sequence of pipe repairs in an earthquake damaged water network that minimizes the cumulative loss. That would be an example of a reinforcement learning, or a problem that could be tackled by reinforcement learning. In terms of supervised learning, which I think is the one that we're most familiar with in our community and the one that we use the most, there's regression. So this is where you actually have a response variable that's continuous. So for example, the example I talked about before, the drift capacity of reinforced concrete walls, drift demands in frames, collapse capacity, all of those are examples of things that could be dealt with regression, or you could view as regression problems. There's also classification. So this is where your output is actually a categorical variable. So for example, if you're trying to predict the damage state of a structure or the failure mode of a particular structure, these would be classification problems. So getting in more into some of the opportunities, and the way I'm going to frame it is I'm going to sort of ask or talk a little bit about when you should be considering using machine learning in structural engineering, right? And so the first context here I say is if you were going to use an empirical model anyway, right? So as I mentioned before, within structural engineering, we make use of engineering models that are largely informed by physics, but it's often the case that the physics-based relationship, either we do not have explicit physics-based relationships, or the physics-based relationships we know that they don't capture all the important phenomena that are in there. So in those cases, we would do physical experiments, and we would take that empirical data and we would use basic statistics to develop some type of regression model, right? And so machine learning models are basically empirical models. They are data-driven models. So if you were going to use an empirical model anyway, then it might be worthwhile to consider machine learning. So this is an example here where we were interested in looking at predicting the drift capacity of reinforced concrete walls with special boundary elements with machine learning, right? So there was a study that was done by Abdullah and Wallace. Professor Wallace is one of my collaborators at UCLA. They developed an empirical equation to predict the drift capacities of special boundary element walls. And they used a data set of about 164 tests. That sub data set is part of a larger data set of over 1,000 walls. And they developed a fairly simple an equation based on linear regression, where the parameters that they consider are things like the slenderness ratio. The alpha parameter is related to the configuration of the stirrups, and then the shear stress demand as well as the concrete strength. But upon further examination of the relationships between these parameters and the drift capacity, we found that there's actually a lot of nonlinearity in those relationships. So we wanted to explore whether or not any benefit can be derived from using machine learning to develop this type of predictive model. I'm not going to go into all of the details. We have a paper here that was put out as part of the special issue that Professor Nassar mentioned, but I am just gonna talk a little bit about the results that we found. So what we're looking at here is, this is actually based on the training data. So the typical workflow in developing a machine learning model is you want to quantify the performance of your model using what's called the out of sample error, meaning using data that the machine learning model has not yet seen. This is actually based on the training data. We'll talk about the out of sample error a little bit later, right? So here we're comparing the performance of what's called an XG boost model. So this is an extreme gradient boosting model. And again, in the interest of time, I'm not going to go into the details, but I'm happy to answer questions about it. And just visually, and also based on some of the performance metrics that are shown there, we see that we can get some improvement in terms of predictive performance. So for example, there's a metric there shown as D subscript 10%, 10%. So this is basically the fraction of data points where, or you can think of this as the probability that the prediction that you get from the model is within 10% of the observed prediction, right? So this is 76% for the XGBoost model. It's 53% for the Abdallah and Wallace model, right? So we're seeing some improvement there in terms of predictive performance. Now, one of the things we need to keep in mind in developing machine learning models, we need to worry about overfitting models, and that's something I'll talk a little bit about later. And one of the ways we try to address that is by looking at this out of sample performance, right? So what's shown in the table below is the performance specifically of the XGBoost model on the training set, meaning the data that was used to develop the model, and on the testing set, meaning a subset of that data that was held out, so the model it was not included as part of the training process. And if you talk to a statistician, what they will tell you is, to not have an overfitted model, you pretty much want to get comparative performance within your training and testing set. So it's interesting here that if we compare, say, the D25% in the training and testing, it's fairly comparable. But when you go to the D10%, meaning you have tighter tolerance on what you would consider acceptable, there is some difference, 59% versus 76%. And we can argue about whether or not that's close enough to warrant saying that our model is not overfitted. But again, I'm happy to answer questions on that later on. Moving on. So again, we're asking the question here: when should you consider should you consider using machine learning in structural engineering? Well, there are certain situations where the use of machine learning models can provide some benefits in terms of time savings. And so that's something that's worthwhile exploring. And that's something that we as a research group have been exploring. And one context we've been exploring that is in the context of performance-based seismic design. And what's shown here is the typical performance-based seismic design framework that's taken directly from the FEMA P58 document. And the procedure basically goes by, you define your performance objective. These objectives could be based on different metrics. It could be based on reliability. It could be based on resilience. It could be based on life cycle costs. Once you have that performance objective, you would do some preliminary design. Then you would assess the performance of that design. If it meets the objectives, you finalize the design. If it doesn't, then you would revise the design and you sort of repeat that loop until you achieve the target objective. Now, if you're doing sort of what I consider the second generation performance-based earthquake engineering framework, where you have to do nonlinear response history analyses and damage and loss assessment, there's sort of this iterative process that you have to do things that are fairly computationally expensive, right? So you're building nonlinear structural models, you're analyzing them, and you're feeding them into the FEMA P58 loss assessment framework. That could get computationally expensive. So one of the things that we've been exploring is using surrogate models to do that iteration, right? So you utilize surrogate models, and I'll talk a little bit about what they are, but essentially what they're doing is they're basically short-circuiting, at least within the iterative portion, part of that explicit either nonlinear analysis or loss assessment, right? And you would basically use those models to find your target region, right? So the region within which you think your design is desirable or optimal. And then once you find that region, then you can perform your final design. And the idea here is that you would reduce the number of explicit iterations using the surrogate model, right? And so the question is, what is a surrogate model? Well, it's basically a statistical or a machine learning model that's intended to mimic some type of mechanistic relationship. In this case, it could be the responses that you get from nonlinear response history analysis. It could also be it could also extend into the physical damage and loss assessment that you get from the FEMA P58 methodology. And so we've been exploring developing such models specifically for seismic demand estimation. And without going into a lot of the details, we've sort of conceived of this spectrum of possibilities within which you can develop these surrogate models, where on the left end, it could be based on purely on mechanics, right? So this is sort of the more traditional approach where you use just engineering principles to develop some simplified model for estimating drift demands. And on the right end, you have a purely data-driven model. So this is a model where you would do parametric nonlinear responses tree analyses. You would fit some type of machine learning model to that. And to use it, you would just put in the relevant input data and you would get the responses. And then somewhere in between those two extremes, you have what we call a hybrid model. So this is a model where you have some mechanics-based relationship that you're working with, but maybe you're utilizing the machine learning model to get you, say, from linear response analysis, linear static response analysis to nonlinear dynamic response analysis, right? So that's sort of a hybrid approach to thinking about these surrogate models. So going back to our original question, when should we consider using machine learning in structural engineering? Here I say when your physics-based model is incomplete. And I sort of alluded to that before, right? So again, a lot of times our engineering models are informed by physics, but in many cases, these models are imperfect. Either they're parameters that are not included that would actually affect the behavior, or there's a calibration process that's needed such that the physics-based relationship isn't complete in that sense. And here I'm gonna pick on hazards because we're focusing specifically on classifying damage to building portfolios. Right. And so the idea here is that we know hazards does have some physics-based relationships built into it. It's fairly simplistic, but you can argue it is based on some physics. And so the question becomes, can machine learning serve as a replacement to a hazards type model, given the level of simplification that's needed, and the fact that there is also some empirical basis in hazards as well. So we implemented this study where we use machine learning to predict the damage, the tags, the ATC20 tags that are developed after an earthquake using inspections. Really quickly, we used different types of features related to the earthquake, related to the site, related to the building itself. We looked at a number of different algorithms. The random forest algorithm is the one that ended up performing the best. And we also looked at which of the features had the highest influence on the performance. In the interest of time, again, I'm not going to go into the details, but I would say that the overall accuracy we got was 66% on the testing set. Again, we're doing that training testing split. And so one question you can ask is, what would the performance have been if we would have done this using hazards? And that's not a question that we've answered, but it's certainly one that's worth exploring. And so the last sort of point on this question of when should we consider using machine learning is if it creates new opportunities. So in this particular case, we actually trained what's called a long short-term memory model to predict the tags using the written descriptions of damage. So this is something that could not have been done without machine learning. Okay, so as I mentioned before, machine learning is not without its challenges. So I'll sort of talk a little bit about some of those challenges. There's issues with data sparsity, accessibility, and overall quality, right? We hear a lot about big data and the use of big data. Well, within structural engineering, the data sets that we have generally don't qualify for as big data in the context of if you're looking at images and large text and things like that. So that's something that we need to think about. We certainly need to build some consensus about what methods are most appropriate for the field. If you look at different studies, people are choosing to use different methods for different reasons. A lot of it is just based on familiarity. So I think we need to sort of study which methods are most suitable for which problems. I mentioned the issue with interpretability, right? So in a lot of cases, these machine learning models, even the ones that we understand, for example, random forest, we actually know how they work, but it's in terms of describing the model itself, it's not a model that can be written down. And so there's challenges with interpreting the results. But these are challenges that can be overcome with some of the right approaches that I'll talk about later. There's issues with overfitting, right? So we always have to be mindful of the fact that these models, as we increase their complexity, there's chances that we're overfitting the models. And so we can address that using that training, testing, split, and some other techniques that are out there. And then this one, there's obviously one of the reasons for this session. There's lack of familiarity. I would say there's growing familiarity within the structural engineering community, and there's a need to build trust within the community, and that's something that we're gonna continue doing. As we think to the future, some of the things we want to focus on, we want to bring some clarity about when machine learning actually provides real benefits, and we're not just using it just because it's sort of the thing to do. We need to be more systematic in terms of collecting, curating, and sharing data, and that's actually happening right now with platforms like DesignSafe and the Rapid Center that have been developed to help with data collection and sharing. I mentioned before that within structural engineering, the data sets that we have are generally smaller, and so there are specific techniques that are geared towards smaller data sets. So we should be looking into those specific techniques. We should be looking at doing comparative assessments across different machine learning methods, as well as traditional methods, to see if there are actually benefits in terms of predicting performance. And then we want to be sure that we're developing models that, to the best extent possible, are explainable. And we talk a little bit about that in the paper that was published as part of the proceedings. We don't want to lose sight or turn a blind eye to uncertainty, right? So we know uncertainty is there. It's something, especially within performance-based engineering, we spend a lot of time characterizing uncertainty. In machine learning models, there's an emphasis on predictive accuracy. So sometimes there can be sort of a lack of focus on uncertainty and the fact that it's there. So that's something that we want to be mindful of. And then we always want to compare our model, do that in sample and out of sample performance. And we want to continue the dialogue. I'd like to think that this session is part of a dialogue that's going to be ongoing. We want to demand transparency to the extent possible about these models and how they work. And to end, I'd say we'd like to introduce data science courses into civil and structural engineering curriculum. So, for example, at UCLA, within the last couple of years, we've introduced a course on machine learning applications in civil engineering that I think will go a long way in introducing sort of the new generation of structural engineers to these methods.